Okay, right. So this particular session, we will go through um, the example of a rocket propulsion example. So I assume all of you have already looked into or watched the YouTube video. Okay, we have, I think there are six video with regards to rocket propulsion. The first three videos telling on or showing the basic rocket propulsion fundamentals, and then the video number 4, 5, and 6 showing the fundamentals, the important parameters that normally being used for rocket propulsion. Okay, for this particular exercise, I hope you have your pen and pencil or of paper, okay, to jot it down. Um, it is also, you can always refer to the equation provided from the YouTube video. Later you can watch this recording again. So in this particular problem, we have a rocket missile, okay, which has the following characteristics. So we have an initial mass. The rocket missile has an initial mass of 200 kilogram, and then it has a mass after rocket operation. So once the rocket has already used the propellant, the mass after rocket operation become 130 kilograms. So there are 70 kilogram already being used up. Okay, and then the payload itself, the non-propulsive structure on the rocket is 110 kilogram, and the rocket operating duration is 3 seconds, right? See, this is the duration of the rocket in operation. So this is the T. And then the average specific impulse of the propellant is 240 seconds, right? So what you need to do, normally in this type of question, it will guide you to find a few parameters, like what we have already covered in our previous video, that you has already introduced to calculate the vehicle mass ratio, the MR, and then you can calculate the propellant mass fraction, all right, and then propellant flow rate, the thrust to weight ratio, acceleration of vehicle, effective exhaust velocity, total impulse, and finally the impulse to weight ratio. So basically, the question, this type of question will guide you to find the it is kind of like step by step. So it start with the vehicle mass ratio. Once you calculate vehicle mass ratio, then you can calculate the propellant mass until the final one, impulse to weight ratio. And normally we have to make assumption. What are the assumptions, right? So in this particular rocket propulsion, normally any rocket propulsion problems, we simplify the situation. We simplify the situation in such a way that we neglect the start and stop transient, right? So normally in the real case for any rocket propulsion, you have to take into account the start and stop transient. It is not instantaneous, right? So they must be, it start from zero, so it will jump to a certain value. For example, temperature value, or the time even, it is not from zero suddenly 100 degrees Celsius, or from zero suddenly 1200 degrees Celsius. It has a graph, it has a curve. So that's why in this particular situation, we simplify, and we assume the start and stop transient are negligible. That's number one. Okay, and then number two is that we assume the thrust produced from the rocket system, in this particular case, the rocket missile, uh, remain constant. So the thrust is remain constant throughout the duration. The duration is 3 seconds. All right. I hope you can take note on that. right? And now let us calculate together the from 1 until number 9. Okay, so in terms of the first one, it asks us to calculate the mass ratio of vehicle, the MR. So MF over M naught, right? What is MF? What is M naught? Anybody can tell me? MF is the
Mass after rocket operation.
mass of the
After rocket operation.
after rocket operation, and M naught is the initial mass. So can we calculate it? What is the value?
0.65.
0.65, right? So we have given 130 for the mass after rocket operation and the mass of the initial, and we have the answer 0.65. I hope everybody can get the same answer, all right? And then we thank you for whoever answered it. I don't know because I cannot see the view. I'm not really familiar with WebEx, but thank you very much for the answer. And then we continue to find the mass ratio of rocket system, right? Just now is the mass ratio of the vehicle, right? This is the whole rocket system, MF over M naught again. What is the value? So let me just go back so that you can jot down this first, because it's very important, because jot down the initial mass on your piece of paper, which is 200 kilogram. I give you some time, right, to write it down now so that we don't have to go back to this particular slide. Initial mass is 200 kilogram. Mass after rocket operation, the 130 kilogram. The payload, take note on the payload value, 110 kilogram, right? Jot it down, and then jot down the rocket operating duration, the T, small t, equal to 3 seconds, and the average specific impulse of the propellant. So the symbol is I subscript S, so IS. So it is the duration, average specific impulse propellant is 240 seconds. Okay, everybody got all the information, the initial information, right? Shall we just go to the slide? Okay, we have already calculated the mass ratio of the vehicle. Now, what is the mass ratio of the rocket system? Anybody has the answer?
0.55.
0.55.
No.
So it is not. So basically, the mass ratio of rocket system, good try. Basically, you have to deduct the value of the mass of the rocket after operation minus the non-propulsive system, 110. So 130 minus 110 divided by 200 minus 110. So you will get this value 0.222. Okay. So any questions so far? All right. If not, you can jot it down, but you can look at the video later on if you don't want to jot it down. But I would like everybody to try, because I cannot see whether you are trying or not. But I assume that some of you will try to get the right answer. Tell me if you get a different answer if you put the numbers. Okay, so note that the empty and the initial masses of the propulsion system are 20 and 90 kilogram respectively. So you can calculate it there and you will get those value. Right, shall we just continue to calculate the propellant mass fraction, right? The zeta, zeta equal to m naught minus mf divided by m naught. It's quite straightforward. Just plug in the number. What is the answer? Anyone?
35, Doctor.
Pardon? 3?
5.
35. So it is M naught is 90. Okay, just now if we still remember, okay, the empty and the initial masses of the propulsion system, it is the propulsion system, 20 kilogram, and initial masses is 90 kilogram. So propellant mass fraction is 90 minus 20 divided by 90. So zeta is 0.778. Okay, so then you can calculate the propellant mass, the MP, before you calculate the mass flow rate.
10.
What is MP? What is the value of MP? Anybody would like to try?
10, Doctor.
Pardon?
0.
0.
110.
0110. So it is propellant mass is just simply 70 kilogram. Because let me just go back to the, probably it's quite strange because we have to go back and forth, and so initial mass is 200 kilo, mass after rocket operation is 130, basically 70 kilo of propellant being burned. Okay, there's no trick question there, and it's just straightforward. 200 kilo minus 130, so the mass of the propellant is 70 kilo. So the propellant mass flow rate, the M dot, is what? What is the equation for M dot?
Mass over time.
Mass over time. And what is the value?
70 over 3.
70 over 3, you will get
23.33.
23.33. Very good. So basically, M dot is the mass flow rate for the propellant, 70 kilogram divided by the time. Time is 3 seconds. So you get 23.3 kilogram per second. Make sure you put down the unit wherever needed. For example, like propellant mass, make sure you have the kilogram there. For mass flow rate, make sure you have kilogram per second. Okay. Is it okay to go to the next slide so that we can appreciate more? Never mind if you still figure out, wait, why is it this value? Why is it that value? Probably later on you can appreciate the solution that I'm sharing. Right. Now, let us calculate the thrust. The thrust normally being used, the symbol is F, and we know that the thrust equal to the specific impulse, IS, times the W dot. So, okay, what is W dot? The weight. So it's not the mass flow. This is the W dot. Okay, what is the value now? The thrust value of the thrust now equal to any answer?
$55,000.
Okay, 55,000. Is it a round number, or you have some values there?
54,857.
Okay, 54,857. Excellent answer. So basically, you have the impulse value, specific impulse value, the 240 times the 23.3. Okay, this is the m dot, m dot mass flow, propellant mass flow, and then the gravitational acceleration. So that's why you have the weight there. So you have the value of the thrust of the rocket propellant is 54,857, and the unit is Newton. Now you can calculate the thrust to weight ratio of the vehicle, right? So you have the initial value for the thrust to weight ratio. So you just put in the number of the initial weight, and then the final value you put the number of the final weight. So F over initial weight, F over the thrust value over the final weight. Okay. So there should be two answers here. Anybody would like to try? I hope everybody is trying to calculate the problem, and then any answer for the initial thrust to weight ratio of the vehicle, and then a final value of thrust to weight ratio of the vehicle.
27.96.
27.96, and then it is it is about around 28. Okay, and then the final value,
$43, doctor.
43. Yes, 43. So correct answer. So the thrust to weight ratio, it doesn't have the unit. So make sure you don't just simply put Newton or whatever. Make sure you know for the thrust you have the unit Newton, but the thrust to weight ratio, it is already being cancelled out. Okay, so we go to the next slide. Now you can calculate the maximum acceleration of the missile, rocket missile. Normally acceleration is small a, right? Don't just simply put capital A. Capital A stand for what?
Area.
Area, yes. Capital A stand for area, and acceleration normally we use a symbol small a. Okay, what is the value of the maximum acceleration?
No.
Pardon? What is the answer? Anyone? Anybody?
Doctor.
Yeah. Any answer on
Guessing 274.
pardon?
274.
274 meter per square second, right? It's not, right? It's you have to 43 is what is the value of 43 just now?
Thrust weight ratio of final.
Yes, so times the gravitational acceleration. So you will get the maximum acceleration possible for the rocket missile. The unit is meter per square second. I'm very sorry. Some of you putting in the chat note, okay, but since when I when I view the slideshow for the presentation, I cannot see the slide. Sorry, I cannot see the chat box. I don't know how I'm going to put it in front. Okay, I cannot. I don't know how. Never mind. So, but feel free to just shout, and then I can hear your voice so that you can ask me to go back to the previous slide. I'm very sorry just now. It's already 10 minutes. The message is 10 minutes ago. So let us continue to find the effective exhaust velocity. Effective exhaust velocity C, right? Which is equal to the specific impulse is time the gravitational acceleration. So you will get a value of exhaust velocity that come out from the rocket.
The G naught is 9.81, is it?
Yes.
So the answer 2354.
2354 meter per second. Make sure you put meter per second. If you just put 2354, okay, even though the numbers is correct, but you don't have unit, you don't get, and your answer is wrong. Right? So make sure everything is unit is correct. If you have a decimal or whatever, just put 2 decimal places. Don't put until 4 or 5 decimal places. Just put 2 decimal places. Okay, thank you for the answer. And now you can then calculate the total impulse. Just now is a specific impulse, IS. So the total impulse, the symbol is I subscript T, which is equal to the specific impulse time the weight. So I just put the note here. This result can also be obtained by multiplying the thrust value. You have the F value with the thrust duration. So basically 54,000 plus times 3. So you will get the same answer for the total impulse, which is equal to 164,808 Newton second. Okay. So you have the value of specific impulse 240 second that already been given earlier, right? So you have the value of the 70 is the value of the propellant mass, 70 times the gravitational acceleration. So you will get this value. At the same time, if you multiply the thrust value with the thrust duration, you also will get 164,808 Newton second.
Doctor,
Yes.
the thrust value is 54857 Newton, is it?
Yes. Yeah.
Multiplied by 3, I got 164571. Is it okay?
Yes, it is approximate.
Alright, okay.
Yeah.
Thank you.
You're most welcome. Right. And then, okay, I'm very sorry. So there's the impulse to weight ratio of the propulsion system, IT divided by W naught, the initial weight, impulse to weight ratio of the propulsion system. So you will get, you plug in the number IT, right? The total impulse just now 164,000. Is it 164? 164,000. Okay, divided by the initial weight. So the value would be 187, right? So okay, so in summary, the final answer that being asked in this particular question, right? It asks us to calculate the vehicle mass ratio. So we have the vehicle mass ratio value, we have the propellant mass fraction value, propellant flow rate value, the thrust value, thrust to weight ratio, okay, the initial and the final, and acceleration of the vehicle, effective exhaust velocity, And finally, the total impulse and impulse to weight ratio, right? So it's not that difficult, and it's quite straightforward in terms of the uh, equation, right? And what you need to do, as I said earlier in our course, if you still remember that I mentioned that the equations are going to be given, meaning that you don't have to memorize. If you memorize the equation, is even better, because it's not that complex, and you will save time in order for you to put the correct values, right? So any questions so far? Let me just stop sharing. All right. Any questions so far? Now we have 33 students. All right. Thank you for being here. Any questions so far with regards to the example given? Okay. Let me just stop recording.